I'm going to talk about my joint work with Seljuk Aygin. He's a PIMS postdoc at the University of Calgary, working with Juan Nguyen. Seljuk was a postdoc, PIMS postdoc in the University of Lethbridge last year, and we started working on this project together. So the title of the project is Sums of Triangular Numbers and Sums of Squares. So let me start with some kind of historical background on this subject. This is a very kind of old topic. So the main function that we have, and we want to study this function RSN, which is basically count the number of representations of n as sum of s squares. This is a very classical function, well studied for several centuries. And there were some major results 100 years ago, which actually I'm going to review some of them. So just give you an idea. Now 5 can be written as sum of two squares in 8 different ways, as I demonstrated here. And so therefore R2 of 5 is going to be 8. And you can ask, for example, what is R2 of 2021? How many ways we can write the and 2021 as sum of two squares. So if you know, you know. If you don't know, you're going to see it actually in the next few slides. Okay. So there are lots of problems we can formulate on this problem. The one that I am actually interested in is the following. We like to find, so this function RSN is very kind of irregular, and we like to express RSN in terms of some known arithmetic functions, some simpler arithmetic function, like for example, sum of divisors functions and so on. So we like to get handle of RSN by expressing it as a simple, some simpler arithmetic functions. So to give you some example of such formulas, probably the oldest one is due to Jacobi, called Jacobi two square theorem. To describe this, I have to consider these two functions d1n and d3n. d1n is a number of divisors of n in the form of 4n plus 1, and d3n is a number of divisors of n in the form of 4n plus 3. And Jacobi proved that R2n is 4 times d1n minus d3n. So the 4 times the difference of the number of divisors of n in the form of 4n plus 1 minus number of divisors of 4n plus 3. So the question that I raised about R2 2021, R2 of 2021, 2021 is a product of 2 consecutive numbers, 43 and 47. And so we have 4 divisors, 2 of them are in the form of 4n plus 1, 2 of them in the form of 4n plus 3. So actually, there's no way we can represent 2021 as sum of two squares. How Jacobi proved this? So the main object that actually, the main tool that he used is something that we call it theta function, which is the generating function of squares. So if here x is just a variable, and if you consider this infinite series x to the power n squares, you get this generating function. You raise it to the power 2, you see that the coefficients are going to basically be this function. Coefficient of x to the power n is going to be R2 of n. So he was able to actually express theta squared x as in this form of this series. They call it the Lambert series. And now if you expand this series, this x over 1 minus x and x cubed over minus x, so if you expand them and you find the coefficient of x to the power n, you get the Jacobi's two-square theorem. Similarly, for theta to the power 4, he found this nice expression. And now again, if we do the same thing, if you find the coefficient of x to the power n here, we get the Jacobi's 4 squares theorem. So what is the 4 square theorem? So this is, I have to introduce 2 functions. One is sigma n, the sum of divisors of n, and the other one sigma odd of n, the sum of odd divisors of n. So Jacobi's 4-square theorem states that if n is odd, R4 of n is going to be 8 times sigma of n. And if n is even, then R4 of n is going to be 24 times sigma odd of n. So give you some examples here. R4 of 2n plus 1, 2n plus 1 is R, so it's going to be 8 times of sigma 2n plus 1. R4 of 8n plus 1 is going to be R4 of 4 times 2n plus 1. So it's going to be 24 times odd divisors of 4 times 2n plus 1. But all odd divisors of 4 times 2n plus 1 are divisors of 2n plus 1. So you get 24 sigma 2n plus 1. And here we can see that we get this nice identity. R4 of 8n plus 4 is going to be 3 times R4 of 2n plus 1. Okay, so here I want to actually have a digression and state something that later I need. So I'm going to introduce this new function R4 star of n, which is the number of ways that you can write n as sum of 4 squares. But here I have this condition that which components is odd, the number of ways that you can write n as 4 odd squares. Okay, a couple of kind of trivial or straightforward observation. Any integer mod 8 either is going to be congruent to 1, 0, or 4. If it's even, it's going to be 0 or 4. If it's odd, it's going to be square of that is going to be 8. Is going to be 1 mod 8. Okay. So the number of ways that we can write this number 8n plus 4 as sum of 4 squares is going to be the number of ways that we can write 8n plus 4 as sum of 4 odd squares. And then here we can check that actually, if we are not in this case, then all of other 4 components should be even. So all of them are going to be even. You square them divided by 4. So if you divide 8n plus 4 by 4, you get 2n plus 4. So the remaining things is going to be the number of ways that you can write 2n plus 2, 2n plus 1 as a sum of 4 squares. But in the previous slide, we showed that R4 of 8n plus 4 is going to be 3 times R4 of 2n plus 1. So from here, actually, we get this identity. R4 of 2n plus 1 is going to be half of R4 star of 8 plus 1. So what does it mean? It means that the number of representation of an odd number as a sum of 4 squares is half of the number of representation of 4 times that number as a sum of 4 odd squares. So we are going to use this somewhere later. So I thought that actually it's a good time to introduce it here. Let's go back to our discussion. So Jacobi also found formula for 6, 8, and you will find the formula for 10. Eisenstein find for 12. The formula actually gets more complicated when S grows. Also, there were some formulas for the case of S odd, but they were not as kind of easy as the case of even. So what was the next major kind of result? So the next major result was due to Ramanujan about like 100 years ago. He considered the case of S equal to 24. And to describe it, I have to introduce these two functions, sigma 11 star of n, which is going to be, if n is odd, is going to be the sum of the 11 powers of divisor of n. And if n is even, it's going to be the sum of odd even divisors of n to the power 11 minus the sum of odd divisors of n to the power 11. And Ramanujan's remarkable result is the following, that R24n is going to be this multiple of this function sigma 11 star plus this error term, he denoted by E24. And then he also proved that this E24, this error part, is going to be represented in terms of a function, the function tau, which is the famous Ramanujan's tau function. Moreover, he proved that for the case that we have an even number of terms, so the case of R2Sn, in general, we can get a main term, which main term actually is a divisor type function. He denoted it by delta. and an error term, which error term is an error term, so it's going to be the little o of this delta part. So he proved this using kind of some Lambert series identities and so on. Okay, so in general, actually, in this problem, it is known that the RSN can be decomposed to two parts. There is a divisor part and there is an error part, and the dominant part is the divisor part. Okay, so the next major development was done by Hardy and also independently by Mordell. So they used the Hardy-Littlewood circle method, and they could find, for S bigger than or equal to, find an exact expression for the delta part using the singularity of certain complex function. So the formula that they find is the following. It's a kind of quite amazing formula. So RSN is going to be written in the form of, so this part is the completely concrete part in terms of pi and the gamma function, and this polynomial n to the power s over 2. And then here you have a series, and this is the singular series, which is an infinite series basically, and each term actually the sum of this exponential sum, which has its coefficient. Each coefficient here is going to be an exponential sum to the power s2, and then we have the error term. So the delta part actually is going to be this first part. So the very amazing thing was that Hardy could evaluate in this problem, he could evaluate because actually he could show that this series is multiplicative, and so therefore you can write it as a product and you can bound it and you can evaluate in a specific case, and you could prove the results similar to the Ramanujan result. Okay, so that's kind of the end of my historical introduction. Actually, it's not the end. I forgot there is another part I have to talk about it. So before ending, let's talk about the triangular numbers. So the case that I consider RSN is a specific example of you writing n as a sum of s squares. So basically, you are interested in the integer value of a quadratic polynomial, and you can change that quadratic polynomial with some other quadratic polynomial. Another example is you can consider basically in how many ways you can write n as a sum of as a value of this polynomial. Each term here is xi times xi minus 1 over 2 is actually something that we call a triangular number. So in how many ways we can write n as a sum of s triangular numbers. Okay, so there is a close relation between this problem and the previous problem, and the relation comes from the following. If you consider this equation n equal to the sum of these triangular numbers, you multiply two sides by 8 and add s to it, you get basically this equation. You get 2xi minus 1 squared, sum of them. So therefore, the number of ways that you can write n as a sum of s triangular numbers is going to be the same as the number of ways that you can write 8n plus s as a sum of s odd integer. So that was the function r star, the number of ways that you can write 8n plus s as a sum of s odd integer, s odd integer is going to be the same as tsn. So therefore, we can see that there is a relation. So the number of representation of integer as a sum of triangular numbers is related to the number of representation of an arithmetic progression. By arithmetic progression means that this 8n plus s as a sum of odd squares. Also, the number tsn also can be described as a number of lattice points on this ellipsoid. And as I said, these are just kind of a typical examples of writing a number as a value of a quadratic polynomials. So there are lots of problems like this we can state, but here in this talk we are focusing on triangular numbers and also the sum of the squares. Okay, so this was kind of the end of the historical introduction. So what I want to do now in this talk, I want to describe the method for computing the delta part without appealing to the singular series. So more kind of, I want to describe a more arithmetic way to deal with the delta part without going through that analytic um, similar series. And I think the best way to do this is that I consider a specific example, and I consider these functions, these two functions, RABN and TABN, which is kind of the next kind of typical problems that we can consider related to RSN and TSN. So I'm going to consider the number of ways that we can write n as a sum of a squares plus the sum of 3 times b squares. So we call this function as RABN. And similarly, we consider TAB as a number of ways that you can write n as a sum of a triangular numbers plus 3 times b, b of 3 times triangular numbers. So there is a literature on this type of problem, and I'm going to refer to it later. But here I'm going to introduce two more kind of auxiliary related function. One is this function R star ABN, which probably you can guess what is it. It is the number of representation of n as a sum of odd squares. So all the components are odd, and the coefficients can be 1 and 3, 1 a times and 3 b times. And then this function R tilde, which is the number of representation of n as a sum of squares with coefficient 1 and 3, a of 1s and also p of 3s. But here we are assuming that at least one of the components is odd. So at least one of them is odd. So 4 functions I defined, R, R star, R tilde, and T, and there are relations between them. So let's, next slide actually summarize this relation. So R star is less than or equal to R tilde, less than or equal to R. So in R star, we have the most number of restriction, as we described before. The number of the ways that we can write n as a sum of triangular numbers is going to be R star of this 8n plus a plus 3b, with number of ways that we can write 8n plus a plus 3b as the sum of a odd numbers, it's the sum of a and b odd squares. And for R tilde, we can see that we have 2 possibilities. If a plus 3b is not congruent to 0 mod 4, if 4 doesn't divide a plus 3b, automatically, so in that case, 8n plus a plus 3b is not going to be even, it's going to be odd. And so therefore, for sure, one of the components in any representation, one of the component is going to be odd. So in that case, R tilde is going to be the same as R. But if 8 plus 3b is a multiple of 4, then we have the total number of representation, we denote it by R, and we have to subtract the total number of representation that all the components are even. But if all the components are even, square of them are going to be divisible by 4, and you divide 2 sides by 4, the number of ways of that all the components are even, it's going to be RAB of 8n plus a plus 3b divided by 4. Okay, so we have these relations, and the questions that we can ask, for example, what we can say about these proportions. What can we say about the proportion R star over R and R star over R tilde? And joint work with Seljuk Aygin, University of Calgary, we could prove the following. So suppose A is bigger than 1, B is bigger than or equal to 0, and A plus B is an even number. Assume that A plus B is bigger than or equal to 4. For the quotient R star over R, if A plus 3B is not divisible by 8, we can say that this limit exists, and it's going to be this value. So we can compute this limit. If A plus 3B is a multiple of 4, we can consider that the limit R star over R tilde, and again, the limit exists, and we can compute the limit in this case too. There is one case here actually is missing, the case that actually 8 divides a plus 3b, what can we say about that? So for that case, we can say that the limit doesn't exist. So r star over r as n goes to infinity doesn't have a limit. More precisely, we can see that if you fix this non-negative integer nu and look at all those integer n such that 8n plus a plus 3b is divisible by 2 to the power nu exactly. So the multiplicity of 2 in these numbers is exactly nu. If you look at this subsequence, this limit is going to exist and is going to be basically 2 divided by this specific number times a factor delta AB and nu, which actually we computed this factor, but here I'm not going to write it. But the main point that I want to make here is that this factor delta, it depends on nu. And so therefore, over this subsequence, the limit exists, but over all the integer, as nu varies, the limit does not exist. Okay, so you may ask that why we consider this problem, why this limit. So the reason is that, as I said, there is a history related to that. And here I want to talk about some background about this problem. So this problem goes back to 1998, where in a paper, Bateman-Knopp, they proved the following relation between R and R star. So they proved that if A is between 1 and 7, then R is going to be this constant multiple of R star. So the number of representation of 8n plus a as a sum of a squares is related to the number of representation of 8n plus a as a sum of a odd squares. Is going to be exactly equal to this. So it's going to be 1. The constant is going to be 1 plus half h is 4. Okay, the proof actually is not very complicated. So let me describe this. The main fact that they use is the following. If a number is odd, the square of that is going to be 1 mod 4, mod 8. If it's even, then the square is going to be 0 or 4. So now if a is going to be 1, 2, or 3, 8n plus a is the sum of a square, all of them should be odd. So therefore, R and R star in this case is going to be the same. Okay, so there is not much to do here. So suppose A is between 3 and 7. So A is 3, 4 is, sorry, here I should say A is bigger than or equal to 4. So suppose A is 4, 5, 6, or 7. And assume that 8n plus a is the sum of a square. Then we have two possibilities. Either all of the squares are odd, or exactly 4 of them are going to be even. Okay? And the rest of them are going to be odd. So again, that simple congruence that I mentioned at the beginning resolves this. So therefore, the number of ways that we can write 8n plus a as a sum of 8 squared is going to be the number of ways that we can write 8n plus a as a sum of a odd squares. Plus, okay, so now I have 4 even squares. So I can have 4 even squares and a minus 4 odd. So there are 8 places there, and then I can actually choose 4 of them as the even ones. So therefore, for the rest, so I have a minus 4 odd ones. So let's call them ki. So you get k1 squared plus k a minus 4 squared less than or equal to 8 plus 4. And now the number of ways, so I have 4 variables remaining here. So the number of ways that we can write, in this case, 8n plus a minus these things, and all the components that I have are going to be, in this case, is going to be even. So I'm going to divide by 4. So this sum is going to be equal to that. So the main observation that we are going to have here, again, for the congruence observation, is that 8n plus a minus k1 squared plus k a minus 1 squared is going to be mod 8 is going to be congruent to 4. So this number is going to be in the form of 8 times L plus 4. So I divide it by 4, I get an odd number. So therefore, this is going to be R4 of something odd. And I remember that you remember at the beginning of the talk, we computed R4 of something odd, and we are going to use here that relation that amounts for half of R star of 4 times that. So therefore, we get this relation. So RA of 8n plus a is going to be R star of that plus half A4, and we have this sum over this R stars. Here, everything is odd, and if you think a little bit here, you think that this sum exactly the same as the number of ways that we can write 8n plus a as a sum of a odd squares. So therefore, this sum is going to be the same as R star of a 8n plus a. If you factor it, you get the result of Bateman-Knopp. Okay, so that's the result. And that's actually the main motivation to consider this problem. 3 years later, in 2001, Bateman, Jacobi, and Knopp, they wrote another paper. Probably this is the last paper of Bateman and Knopp they wrote together. So they showed that actually if a is bigger than or equal to 8, this quotient R over a star is not going to be constant. So this phenomena that we saw from 1 to 7 for 8 is not going to happen for 8, and after that is not going to happen. So therefore, they consider the limit version of it. What can we say about the limit version of it? They prove that if a is not congruent to 0 mod 8, then the limit exists. And if a is a multiple of 8, then they show that this limit doesn't exist. So therefore, as we see, our result is going to give a generalization of this case. So if we put b equal to 0 in our result, we get the result of Bateman, Jacobi, and Knopp. Okay, in 2005, Adiga, Cooper, and Han, they consider again this problem. In fact, they consider all the numbers a and b between such that a plus 3b is between 1 and 7. And they show that actually this relation between R star and R holds. And this coefficient is going to be, this is the quotient that they consider. Their result, in fact, is more general the way that I wrote. They didn't only consider the coefficient 1 and 3. They consider all the partitions that we have from integer from 1 to 7. And in 2008, Berua, Cooper, and Hirschhorn, they consider the case of 8. And in this case, they compare the function R star and the function R tilde. So for the function R, we know that actually this relation does not hold. But if you put R here, but they show that for R tilde, the same thing is going to hold. And again, their result is more general. In fact, they consider all the partitions of A, but here I only consider those partitions that include 1 and 3. Okay, so there is two identities that here we can see, and this is quite interesting. So the result that we got, the limiting results, these are the values that we get at the limit. And for a plus 3b between 1 and 7, this is the value that these other people they got. And you can check actually these two are going to be the same. Similarly, for those values of a and 3b equal to 8, we can see that these two is going to be the same. So our result actually generate this older result too. And it's quite interesting that this side is, you have some combinatoric quantity. So a choose 4 appear here. And the other side, you have some kind of more transcendental quantity, like we have cosine, for example, here. Okay, so that's the result and some background about the result. So now let's kind of start the last part of my talk, which how we prove this result and what is the approach that we can take to study such a problem. So the approach actually is through the modular form and is based on the theta series. But here, the theta series that we're going to consider is not going to be a formal theta series. So let's this theta x was this Jacobi theta series. Let's consider x as q, and q is exponential of 2 pi I z, and z here an element in the upper half plane. Okay, so theta of q is going to have this expansion. It's going to be sum q to the power n squared. And let's consider this arithmetic group gamma naught 4. So these are integer matrices, 2 by 2 integer matrices with determinant equal to 1 and 4 divides 3. And let's consider chi minus 4 be the Kronecker simple attached to discriminant minus 4. And then we can show that now this theta q as a complex function satisfies some very interesting property. In fact, to be a little bit more general, I'm going to consider a special case here, s equal to 4k plus 2, and I'm raising this theta to the power s. So this is going to be the generating function for the sum of s squares if s is going to be in the form of 4k plus 2. Then we can show that this is going to be a modular form of weight 2k plus 1, half of this 4k plus 2, for the group gamma naught 4, and with the character minus 4, chi minus 4. Okay. And there is something more interesting here. If you consider this delta Sn, remember this delta Sn was that values of singular series. If you consider the singular series and you basically consider this infinite series and you form this complex function, you call it sigma s of q, we can show that actually psi sq also is going to be in the same space. It's going to be a modular forms of weight 2k plus 1, level 4, and character pi minus 4. Something more interesting, if you consider the difference between these two, then it's going to be again a modular form, but also it has this special property that it's going to vanishes at all the cost of gamma naught 4. Okay, so I have to say a little bit more about modular form, this was an example. So what is the summary before I start talking about the modular form is the following. The delta part of Rsn, in fact, is the nth coefficient of the Fourier expansion of the Eisenstein component of theta sq. What is the Eisenstein component? The Eisenstein component is basically this psi sq. And let me describe that Eisenstein component more. So to do that, I have to say something about the modular forms. Again, I don't want to describe everything in detail here. So roughly, a modular form f of weight k, level n, and character chi is a holomorphic function defined on the upper half plane that satisfies certain transformation property under gamma naught n and is holomorphic at all the cusps of gamma naught n. If f vanishes at all the cusps, we say that we have a cusp form. Okay, so this is, if you consider the space of all modular forms of it, k, level n, and character chi, we get a complex vector space. You get a finite dimensional complex vector space. And you can have actually an inner product in this space called Peterson inner product. So you denote the cusp space by the space of all the cusp formed by sk, gamma naught n and chi, and the space of modular form as mk of gamma naught and chi, and the orthogonal complement of sk in mk, you call it as ek. And this is something we call it the Eisenstein space, the things that I mentioned in the previous slide. So therefore, any modular form, level n and character chi, weight k, has a unique decomposition as a kind of Eisenstein component, EF, and a cusp component, CF, which EF is going to be in Eisenstein space and CF is going to be in cusp space. Okay, so now we can say that what is going to be delta part. So if you consider the Fourier expansion at infinity of f with the coefficient AFN in this form, so it is the Fourier expansion at infinity for f, for EF also there is a Fourier expansion. For CF, is going to be a Fourier expansion. So for EF now, we consider EFN as the coefficient. So you shouldn't be confused this E with that Ramanujan E. That E there was error, but this E is an Eisenstein coefficient. So basically, the nth Fourier coefficient of F is going to have an Eisenstein component, EFN, and it's going to have a cos component. And we can show that actually the cos component, CFN, is going to be bounded by n to the power k over 2. In majority of the spaces, we're going to see that the dominant part is going to be the Eisenstein part. And this is going to be basically the delta part in the notation of Ramanujan. Okay, so our goal here is to describe how to compute this delta part. And to do that, we have to basically say something about this Eisenstein space. So we know that we can show that the dimension of the Eisenstein space is equal to the number of certain cusps of gamma naught n. The total number of cusps of gamma naught n is going to be this sum. This phi is the Euler function. It's going to be sum of overall divisors of n, GCD of dn over nd, phi of that. So this many cusps we have, and then the dimension of the Eisenstein space is going to be smaller than that. And then also we can describe an explicit base for this Eisenstein space. And to do that, you have to describe weight k Eisenstein series. The weight k Eisenstein series associated with the Dirichlet character epsilon and psi is denoted by the following. It's going to be a sum over this generalized divisor function. And then basically we have this series here, and here we have the Kates-Bernoulli number associated with the character chi. So here chi is going to be epsilon times psi. So basically we have to define these generalized divisor functions in terms of epsilon and psi, and then you have this function, and this is going to be in the Eisenstein space. Okay, using this Eisenstein series, we can describe a basis for weight k Eisenstein space of level n and character chi. This is written for the first time in 1977 by Weisinger in his PhD thesis, in Harvard PhD thesis. For k bigger than or equal to 3, he shows that if you consider this scaled version of this Eisenstein series, you form a basis for the Eisenstein space. So this Ek of dz epsilon and psi is going to be basically all the Eisenstein series when epsilon and chi varies over all the character epsilon and psi, such that their product is going to be chi, and their conductor epsilon, conductor psi, times this scale d divides n. If you vary over all this epsilon, psi, and d that satisfy this, you're going to get a basis. Also, he describes the basis for k equal to 1 and k equal to 2. So these bases are well known. Okay, so we know that actually the delta part is living in this Ek. We have this explicit base. So therefore, this is very natural. This is a problem of linear algebra that we try to write the delta part as a linear combination of this base. Okay, so to describe that, I have to introduce one notation. So suppose F is a modular form, A over C is a cusp. So we know that F is going to have an expansion at the cusp over C, and it's going to be holomorphic, so it's going to have a constant. The constant in the Fourier expansion of F at the cusp A over C, we denote it by this notation, bracket 0, A over C, F of C. And this is a kind of a natural procedure that we can consider. A procedure for finding the Eisenstein component of F is the following. We have our bases here, this base that comes from Weisinger's thesis, and we want to write F as a linear combination of this base plus the cusp part, C. Okay, we are going to first compute the constants in the Fourier expansion of F at A over C here. and the constant in the Fourier expansion of E at the cosp A over C. So here you have a constant, here you have a constant. Suppose A over C is fixed. Okay, C over CZ is a cosp form, so therefore the constant is 0. So therefore, for correspond to each cosp, we are going to get, if we can compute the constant of EK and constant of F at the cosp A over C, if we compute them, then we can form this system. Okay, we're going to form this system, and then in a specific problem, we can form this and we try to solve it. If we solve it, then we are done. But in general, is this system solvable? Do you have enough equations to solve this? And is it this solution is easily expressible in terms of the data that we have? We're very fortunate that Seljuk Aygin proved that actually the system in step 3 of this procedure has a unique solution, and also the solution can be expressed in terms of the data in step 1. So this is quite interesting result. So if we can compute the constant F at the cosp A over C, if you can compute them, there is a formula, and this formula is written in this paper. It's quite a complicated formula, but it exists. And then you can basically plug in there, and then the Eisenstein part is going to be computed. So if you want to know, the paper of Seljuk is available in arXiv, so you can look at theorem 3 there. Okay, so now let's finish off with to see how the proof works in our. So remind you of what was our theorem. We were interested in the asymptotic ratio of R star over R and R star over R tilde, and the result was saying that if 8 doesn't divide A plus 3B, the ratio has a limit, and in this case, the ratio all the time has a limit, and if 8 divides A plus 3B, the ratio is not going to have a limit. But if you restrict yourself to this specific subsequences, the ratio is going to exist. Okay, I'm going to just describe the result for the case of R star and R, and just for some, as you see that we have to consider many cases here, so I'm going to just consider kind of the simplest case to give you some idea that how the proof works. Okay, we have basically 4 steps in the proof. First, we have to write the problem in terms of the theta series. So we have to form R star and R corresponding to theta series and locate this in the appropriate space of modular form. Then we have to use Eigen's theorem to explicitly compute the Eisenstein component of this theta series R star and R. Then we have to use the relation that we find to find a relation between the coefficient of Eisenstein components in step 2. And finally, we have to show that the Eisenstein components are dominant and establish the asymptotic result. So let me tell you something about each step. So first, forming the theta series for the problem of the sum of squares. The theta series actually is a kind of classical. It's going to be theta A of Z and theta B of 3Z. You have to scale it by 3 because the coefficient 3 that we have. For the problem of triangular numbers or R star, equivalent to R star, the theta series is a little bit more complicated, can be expressed in terms of this theta series psi. So this is the kind of generating function of the triangular numbers. We scale it by 8, and then we have the theta series for this R star AB 8n plus 8 3b can be written in the form of this product, theta A to the power A, theta A to the power B. Now we have to locate this in a specific space of modular forms. For these psi functions, we are only considered here the case that A plus B is even. If we consider the floor of A plus B over 4 as K, the problem breaks to 4 cases here in terms of the parity of A and B, and also the A plus B mod 4. So this theta function appears in one of these space of modular form. If A and B, both of them are even, A plus B is a multiple of 4, the character is trivial. In the three other cases, we have actually non-trivial character. But all the time, we have real character. Similarly, for the case of the squares, we are going to consider this. So therefore, we have 8 cases that we have to consider. There are 8 distinguished cases that we have to consider. Okay, let's consider the simplest. So there are kind of 8 propositions that is going to come next, but I'm going to just write one of them, the simplest one, the one that's related to this trivial character. So in a step 2, we have to apply the Aygin's theorem, and we compute the Eisenstein component explicitly. And as I said, as long as we can find the constant of this expansion of this theta series at different cusps, then there is a nice formula that Aygin proved. We can just plug in there, and then we get this explicit representation. So this is the explicit representation of the Eisenstein part, and we can do this for all other 8 cases that we have, all other 7 cases that we have. Okay, so what is the situation? So we move to the next step. So the theta series for the problem of triangular numbers for R star can be written in the Eisenstein part. We write it, we get its coefficient alpha n, and also similarly for the sum of the squares, we have this coefficient beta n. And then the cos part, which we denoted by gamma n and gamma n prime, we know that gamma n and gamma n prime are bounded by n to the power a plus b over 4. Okay, so now next, you have to explore a relation between this alpha part and this beta part, the Eisenstein part of each one. And we know that these alpha parts are represented in terms of the generalized divisor function. Similarly, beta is expressed by in terms of the generalized divisor function, and the generalized divisor functions are multiplicative. So we use the multiplicativity and some messy calculation here, and then we show that actually the quotient of this Eisenstein coefficients are going to be equal to this constant. And again, this I just wrote one specific case of this when a plus b is, when a plus 3b is not a multiple of 8. This is not a multiple of 8. Okay, so we have to consider other cases too. Okay. So we come to the kind of the last step here. So we establish this relation between them. Now we want to do the asymptotic. So we have to show that these alphas are large, basically. And more specifically, we showed that this n a plus b over 4 is going to get dominated by alpha. So n to the power a plus b over 4 is going to be little o of this alpha 8 n plus 3b as n goes to infinity. So after showing this, we can put all this thing together, and we can prove that this is actually the first part of our theorem. The theorem has the 3 sections. This is the first part of it. Then we can show that the quotient R star over R is going to be equal to this value that we get. Okay, so I think I used all my 50 minutes. Thank you very much for your attention, and I will be happy to entertain any questions you have. Thank you.
Thank you, Amir. Let's thank Amir for his interesting talk. You can't see it, but you can see me clapping, but you can't hear.
Yes.
So, are there any comments or questions you would like to ask? So while we wait for people to say something, I might add. Very interesting. So the point is, of course, the principle is simple enough, but the details are complicated, aren't they?
Very messy.
Yeah, I can imagine. Yeah.
Yeah. So the idea is basically the linear algebra. I would say that basically the part that maybe is more interesting is this theorem.
Mm-hmm.
So basically, this is the idea. This is linear algebra. We can set up this system of linear equation,
mm-hmm.
and for each specific instance, we can try to solve it if the system is kind of manageable. But the very interesting thing is that it can be, we can find actually an inverse for the coefficient matrix here, or Saljour actually find it.
So that's,
and
that's a general theorem.
Sorry?
That's a general result.
That's a general result, and it can be written, in terms of, so the only information that you need is the constant in this expansion in this cusp. So forget about this problem. If you have another problem, if you have another modular form, and if you can compute this thing, just put it in that, and then Eisenstein part is going to appear. I think this is quite interesting, this part. And then we apply it in this specific problem because of this problem was around, and then we thought that actually but even in this case, as you mentioned, it's quite messy because here you are dealing with the 8 cases.
Right.
Yeah. This method is going to just cover the case A plus B even, because of those Eisenstein bases are known for the case of not having integral weight modular form, for the integer modular form. So if A plus B is odd, in principle, somehow somebody can think about doing it, but then need to find the right bases. And I believe that those right bases are not known, or they are not as nice as the way that is in the case of integral weight modular form.
Very interesting. Very interesting. What do those values look like at the cusps? Are they complicated?
Yeah, actually, I have it here in the paper. I don't know if they look like that.
Okay. I can't see it. It's okay. Okay, so they can be computed.
Yeah, they can be computed. But Saljour actually wrote, if you look at his paper in arXiv, he has a Sage routine. So he actually wrote it in Sage, and then it gives you.
Okay.